Then I will jump into the backscatter communications paradigms and introducing some fundamentals in this research direction. Since this backscatter communication is a basic concept for the smart radio environments, I will talk about the smart radio environments as well. So, and then I will go to some future research directions, which is called NFC-enabled sensor information collection, which I hope that we can have some collaboration in that domain if you are interested in. So, yeah, as an introduction, so it's good to first of all differentiate the differences between the machine-oriented applications, which are standing for machine type communications, and human-oriented applications. So actually, the main difference between the machine type communications and human type communications is that in the machine type communications, or MTC, there is no interaction with the humans. So machines are expected to be able to communicate with each other smartly and without needing any interaction of human. So as you can see here in this figure, there are some applications that are nominated for human-oriented applications and machine-oriented applications. This figure is taken from one of my recent papers, which is IoT IoT connectivity technologies and applications, which is recently published in IEEE Access last February. So as you can see here, there is the difference between the human type communications and machine type communication mainly stands on the data rate. So when we move toward the human-oriented applications, we have smartphones, which requires high data rate communications. And when we move toward the machine-oriented communications, we have such applications like energy and water meters, smart parking, pollution level monitoring, or even waste management. So one thing that it's good to note about is that when we move toward machine type communications, we have a higher density of the applications. So it is supposed that in the near future, we have billions of sensors which are used in different industries, different environments, that the number of sensors is much more than the human type communication devices. So for example, one automotive cars or autonomous vehicles, they are supposed to have many sensors around it to observe the objects around it. So you can imagine that if each car has, for example, 100 sensors, so it will be heaps of sensors that they need to they require some type of satisfactory connectivity technologies to guarantee that the communication takes place perfectly. So here, this figure shows that most of the popular available technologies, connectivity technologies. So as you can see, I classified them in 3 different groups: cellular technologies like 5G, 4G, 3G, and 2G that are mainly somehow conventionally used in these days. So there are another group which is called low power wide area network. So there are some connectivity technologies like LTE-M, narrowband IoT, LoRa, and Sigfox. So on the other hand, we have short range technologies, so which are like Wi-Fi, Bluetooth, Zigbee, Bluetooth low energy, and NFC and RFID technologies. So there are some other technologies that can be considered in these technologies, like in this classification, like Li-Fi. So I just skipped that since it's not yet standardized and largely used in the industry. So one thing that I want to now connect it to this machine type communications towards the backscatter communication is the difference of this RFID and NFC. NFC stands for near field communications, and RFID stands for radio frequency identification. Is that these 2 technologies that are mainly similar to each other are they need the lowest power compared to the other technologies. Somehow they don't need any source of power. They are battery-less devices that can communicate with the other devices. So what makes them very interesting compared to the other technologies is, since that they don't have any source of power, they are very cost efficient compared to the other technologies. So you can imagine that each RFID sensor or each NFC sensor, it costs around maybe a couple of euro cents. So they are super cheap, and it makes them very interesting for some industries and applications like smart retail. You can imagine that currently when you go to the shops or some supermarkets to shop some food or some groceries, you need to stand in the queues and show the items that you have taken, then the cashier will scan all of the barcodes and then give you the price. So but by considering the future smart retails and future supermarkets, this can be done automatically. So when you take the item or you choose that, it can be automatically contact with or communicate with some servers and give you or charge you the amount of money which is the price for that item. So yeah, again, if you need more information for the comparison of these other techniques with these RFID technologies, you can go to this survey paper, and there are definitely more information regarding the rest of the technologies. But for now, I just want to focus on the near field communications and RFID systems, which the backbone for this connectivity technology is the backscatter communication. So again, here there is a table. I don't want to go through the details, but just the reason that I included in this presentation is the valuable information which is provided here. So there is a very thorough classification of the applications versus the nominated or potential connectivity technologies that are suitable for those applications. So here there is a requirements that can cause to different types of classifications. For example, if you take a look at the data rate, we have 3 different classes for the high data rate, medium data rate, and low data rate applications. There are some use cases examples, and then you can take a look at that nominated or potential connectivity technologies for those specific applications. Again, if you need more details, I can just refer you to this paper, which is also open access, so you can easily access that one. So let's jump to the backscatter communication. So actually, what's the backscatter communication? It's very important to know the basics in the backscatter communication. So there are mainly 3 different paradigms for backscatter communication. So the main backscatter communication technology that you are facing in your daily life is when you are going to shop some clothes or some different things from the stores. So you have seen that there are some tags that are attached to the clothes. So when you go, if you don't pay the price of that item, or just take that item and go out of the store, so there is a noise that's called the cashier or the manager by beep beep. So you cannot take any item out of that store without paying the price. So this type of applications are the first paradigm in the backscatter communication, and it backs to around the year 2000. So which was firstly invented and utilized in the Kmart. I think it was Kmart stores. So I don't remember it exactly. But anyway, back to the technical issue. So in the it's called monostatic backscatter communication, the technical terminology. So in those kind of scenarios, we have one reader which has one transmitter and one receiver. So in that case, transmitter will send the interrogation signal towards the one batteryless sensor. So the key idea is that this sensor doesn't have any battery. So then this sensor will somehow modify that interrogation signal or carrier and do some modulation on that, and then send its own data over that signal. So the question that how this device is able to do that returns to the electrical circuit of this sensor, which is mostly related to the electronic guys. So I will just skip that part. Just keep it in mind that this sensor is able, or the chipset in this sensor makes it enable of modifying the receiving signal and retransmitting or backscattering toward the reader. So the second, but there is a problem here. So that problem is for example, self-interference that can be caused because the transmitter and receiver are placed at the same device. So to remove or to enhance the quality of the signal at the receiver, there is another paradigm which is called biostatic backscatter communication. So in that case, they came and separated the emitter. So they have a dedicated emitter separated from the reader or receiver. So it will send the interrogation signal towards the backscatter transmitter and backscatter receiver both. So this signal is known at the reader as well. So and acts like an interrogation signal for this tag, RFID tags. So, and this tag is still able to modulate and retransmit or backscatter that signal towards the receiver. So this is called biostatic communication. So to make it both of these techniques more cost efficient, there is a new concept which has attracted the attention of the researchers in academia and industry recently, which is called ambient backscatter communication. So in that paradigm, there is, as you can see, there is no dedicated emitter. So the emitter here is the ambient RF source. You can imagine that there is a cellular antenna which is communicating with the one legacy receiver here. It's a mobile phone. So in that case, this transmitter is able to hear the signal which is sent towards the legacy receiver. So by receiving that signal, this transmitter is still able to modify that signal and transmit or retransmit or backscatter it towards the receiver or transmitter B. So both of them are supposed that are batteryless and are able to communicate with each other. So this is the idea of the ambient backscatter communication. And since we don't have any dedicated emitter, because mostly these dedicated emitters are they need a source of power. So since we are removing these emitters in the ambient backscatter communication, so the cost will be reduced increasingly. So yeah, these are the three different paradigms, and I want just now to focus on this ambient backscatter communication here, which is an interesting topic and very low cost, very cost efficient connectivity technology these days. So again, here there are some kinds of conventional backscatter communication. As I said, there is a dedicated RF source in the monostatic and biostatic models. So what we don't have this problem in the ambient backscatter communication. In the receiver and the RF source are located at in the same device in the monostatic model, so it causes self-interference. And the other problem of the first two paradigms is that the tag can only transmit data when inquired by or interrogated by the backscatter receiver or emitter. It's better to say emitter. So, but in the ambient backscatter model, since these ambient RF signals are always available around the transmitter is able to decide when it needs to send the data. So it doesn't need to wait for another external source to be activated. So it can automatically send data whenever it wants. So what are the challenges in ambient backscatter communication? Up until now, it seems that everything looks good or the ambient backscatter communication, but this is not the whole story. So the main problem is for the ambient backscatter communication is that there is a in the ambient backscatter communications. So the coverage area is highly limited. So actually, the reader should be very close to the tag to be able to collect data from the tag, because of the specific design of the chipless RFID tags. So another thing which is common for other paradigms as well is the spectral efficiency. So actually, most of the times, these backscatter devices are able to use, for example, on-off king shift, on-off king modulation techniques. And for example, it will make the power of the received signals to zero, or doesn't send anything as a bit 0, or it will retransmit the signal which is received without any modulation, so it will be nominated as 0 at bit 1. So, but it doesn't use the whole spectrum that it receives. For example, you can consider that it will receive one OFDM symbol here in this case. It doesn't use any specific, or better to say that it doesn't exploit the specific structure of the OFDM in the frequency domain. It will just do some modulation on the time domain, and it will backscatter the modulated signal. So it's not spectral efficient. And the third problem, which is specifically for the ambient backscatter communication, is the interference that it may cause for the legacy receiver. So because tag and reader are communicating with each other on the same frequency that is for ambient or the legacy receiver, so it may cause some interferences for the legacy receiver if the legacy receiver is close to the tag. So yeah, to solve this set of problems, or to address at least some solutions for these challenges, I want just to stop at this point and introduce a new emerging technology to you, which the backbone or the backbone structure of that new emerging technology is backscatter communication as well. So, and then I will introduce the difference of the ambient backscatter communication and that new emerging technology, and then I will back to the potential solutions for these challenges. So this new emerging technology is called smart radio environments. There are some other terminologies for that, like reconfigurable intelligent surfaces or intelligent reflected surfaces, meta surfaces, software controlled meta surfaces. All of these terminologies refer to the same concept, which is called smart radio environments. What is this concept? This concept wants to control the scattering, reflection, and refraction characteristics of the radio waves. As you know, the wireless channels are a mixture of these three phenomenon, like scattering, reflection, and refraction, and also diffraction. So the idea is that to design some types of surfaces that can be intelligently controlled or tuned, and then we can have these surfaces over all the objects around us. For example, you can imagine one indoor environments, for example, that are all the walls are equipped with these surfaces. So then when the signals hit these surfaces intelligently control these impinging signals in terms of the phase, in terms of the amplitude, and even polarization. So as you can see in this figure, this is a meta surface or reconfigurable intelligent surface. I can call it reconfigurable intelligent surface. As you can see, there are many sensors on them. So for example, each of these sensors acts like backscatter communication. So they will receive a signal and then they will modify it and reflect it in another direction. So the modification or the modulation which is done here is to change the direction. Okay, so as you know, the Snell's law from your high school. So when some rays or signals hit the ball, it will be reflected in this direction. But with having the intelligent surfaces, we can control this reflection in any direction which is satisfactory for us. So The structure of these metal surfaces is like that. There is a surface which is which contains many sensors, very small sensors, sub-wavelength array of sensors on them. So it's kind of concept. You can imagine some structure like MIMO, but it's definitely different than MIMO. So there are many sensors on the surface that can shape the electromagnetic waves. Again, if you need more, I know that there might be many questions in your mind that about the smart radio environments. So just keep it in your mind that this concept wants to control the wireless channels. And if you need more details about this new concept, this new emerging concept, especially for 6G, you can just go and again access this recently published paper by me in IEEE Access. It was published 2 months ago, which is called RS Assisted Coverage Enhancement in Millimeter Wave Cellular Networks. So it's kind of it has also some kinds of basics and fundamentals of the smart radio environments. So just to give you some hints or insights about the intelligent surfaces, as you can see, this fabricated reflected array is a kind of experimental RIS or reconfigurable intelligence, which is built in a lab in 2016. So as you can see, there are many sensors on it, and it is expected to control the phase of the impinging signal and then reflect it in another direction, or somehow compensate the phase distortion of the signal due to the randomness of the wireless channels. So now back to the direction of our topic about the ambient backscatter communication. So the differences between the ambient backscatter communication and RS is summarized in this table. So the main one difference is about the purpose. So the purpose of the ambient backscatter communication is to transmit data over the ambient RF signals, okay? So, but in reconfigurable intelligent surface, we are not sending a new data. We are just enhancing the signal quality or controlling the wireless channel or controlling the environment in terms of the wireless communication. So the main component in the ambient backscatter communication is just a single backscatter device. But in reconfigurable intelligent surfaces, we have a large number of these large number of reflectors or sensors on a surface. So another difference between the ambient backscatter communication and RIS is the signal modification, which is done in the backscatter communication to send the data. But in the RIS, we are just controlling the phase shifts, for example, to avoid any phase distortion at the receiver. Another thing is that this is a similarity between both of them, which they don't need any type of dedicated energy source, so they are very cost efficient in the long term communications. And about the coding, ambient backscatter communication is able to encode the data, but in reconfigurable intelligence surfaces, we don't have any decoding or encoding. Now back to those challenges that I mentioned in the previous slides about the challenges for the ambient backscatter communication. That one of them was the communication range. So usually these technologies, ambient backscatter communication, needs to have a very short range communication, usually around 10 centimeters up to 1 meter. But by combination of these two technologies, RIS, reconfigurable intelligent surface, and the backscatter communication, ambient backscatter communication, we can somehow overcome the short range communications in the conventional ambient backscatter communication. So as you can see, the scenario is like that. For example, you can assume that we have a Wi-Fi modem here, which transmits ambient OFDM signals towards the one legacy receiver, your cell phone at the home. So there are some walls, indoor walls in your house or apartment or unit. And then there are some tags which are, for example, able to take some measurements like temperature, water meter, or anything. These tags can be any of those, can be used for any of those applications. So These tags as usual since it's a very in a same area which is exposed to the ambient OFDM signal transmitted from the wireless or Wi-Fi. It is able to receive that signal and then backscatter that signal towards the reader. So there are some parameters. I don't want to go towards that parameter, but this is again another solution which is published in one of my conference papers in the WCNC. And it was presented also in WCNC in South Korea. It was in April. So, but by this type of topology, what I want to mention is that by this type of topology, we can have a new distance communication between the tag and reader compared to the old version of the communication without having the RS or reconfigurable intelligent surfaces. So in that case, this QB stands for the number of RS elements or number of sensors on the wall. So if you have for example, if you have, for example, 2 or up to, or let's say 4 sensors over this wall, these 4 sensors can be squared up to 16 times better the coverage area we can have in this topology. So the conclusion would be that the coverage scales up with the square of number of reflectors over the RS walls. So in that case, we can have we can overcome one of the challenges on the ambient backscatter communication by utilizing the reconfigurable intelligent surfaces sooner or later in future. So there are some simulation results here based on the number of reflectors on the RS walls and also attenuation of the line of sight path, paths. So between the OFDM signal and their tag. So with that kind of ratio, we can have a different ratio of the coverage enhancements. For example, if we have 8 reflectors over the RS wall, we can have up to 10 times better coverage area compared to the conventional ambient backscatter communication. So again, in terms of the bit rate performance, we have a better SNR at the receiver, so which caused to have a better better signal quality at the receiver. So again, these are some simulations for different parameters of the number of the RS sensors. So another challenge for the ambient backscatter communication was the spectral inefficiency. So to overcome the spectral efficiency, what I can say at this moment is that definitely we need to have a more advanced structure in the tags, so RFID tags. So the goal is here that assume that the Wi-Fi sends OFDM signals towards the reader. So that OFDM signal has for example, let's say n number of subcarriers. So if what we want to do is to enable the tag to send 1 bit over each of these subcarriers instead of sending 1 bit over the whole OFDM signal, the subcarrier number of subcarriers. So in that case, what I proposed in this paper, subcarrier-wise backscatter communication over ambient OFDM signals for low-power IoT, which is recently published in the IEEE Transaction on Vehicular Technology. You can access that one. So I propose a new design for the tags, RFID tags, which includes a set of bandpass filter banks. So as you can see, by employing a set of bandpass filter banks or even notch filters that are analog filters, we don't need to have any we don't need any type of source of powers. So since they are analog and they are all passive, so they can be employed inside the tag. So in that case, instead of sending one bit over the whole number of subcarriers, we can have up to n bits over the whole OFDM subcarriers. So in that case, we have a huge increase in the spectral efficiency of the backscatter communications. So in that case, we have the improvement in the data rate, satisfaction of the low medium data rate requirements in the low power IoT applications will be guaranteed. So in case that some of the backscatter communications sometimes are incorporated with the very low data rate IoT applications. So in that case, the extra subcarriers can be used as a interleaved block transmission. For example, we can consider a block of subcarriers for just transmitting one bit. So in that case, we can boost the bit error performance, which I called it modification 1 in this case. So by sending one bit at one bit over a block of subcarriers, we can still have a higher data rate compared to the existing method, but also we can improve the bit error rate as well. So, and we can have another modification by using the index modulation in the ambient backscatter communication to somehow reduce the number of active subcarriers. In that case, the third problem, if you remember the third problem, the third challenge in the ambient backscatter communication was that the tag can cause some interference for the legacy receiver. So if we somehow control the number of active subcarriers which are transmitted from the tag toward the reader and the legacy receiver, so by reducing the number of active subcarriers, we can reduce the interference for the legacy receiver. So somehow we can have a very minor control over the interference which may be caused for the legacy receiver. So here there is a simulation for the bit error rate performance of these new techniques using the whole subcarriers that are using the OFDM signal. You can see that compared to the existing methods or conventional method, we can have we can gain around 8 dB SNR gain here, so which is a huge. And if we have we can send more less number of bits over the more number of subcarriers, for example 1 bit over a block of subcarriers, so again we can have a better SNR gain. So the previous one was for the AWGN channel, so somehow it's similar to the AWGN channel, and the third one, this figure is for the Rayleigh fading channel. So again, as you can see, we have in the Rayleigh fading channel, we have a slightly better performance when we are sending 1 bit per subcarrier, but when we send 1 bit per block of subcarriers, again, we have a huge gain in the bit error rate performance. So it gives us some kind of freedom and flexibility to choose to send how many bits per how many subcarriers by deploying the block of subcarrier subcarrier block transmissions or either index modulation transmissions. So in terms of the high data rate ambient backscatter communication which I propose, again there is another comparison in terms of the data rate. So again, this figure, this figure shows is to gives us some kind of flexibility in terms of the data rate, that we can have different number of subcarriers at each block and somehow choose the best option with respect to the application that we want, and then have a satisfactory data rate in that case. So another simulation, due to the lack of time, it's very similar to that one, but in terms of the previous simulation, but it's in terms of the average power. So what it gives us is that it doesn't add much average power compared to the conventional models. But when we use the index modulation with the lower number of subcarriers, we can have a lower average power compared to the conventional models. So the first bar is for the conventional model, which is basic model. The second one is when we have a 1 bit per each subcarrier. The next two ones are for two different block transmissions, and the last three ones are for the index modulation transmission. So that we have a lower number of active subcarriers in those cases. So now about the future directions in the backscatter communication. So actually, one of the big potentials for this backscatter communications is that when we are using this, let's assume that NFC stands for the near field communication. So near field communication is very similar to the RFID technology. So they are in the same family. So one of the big potential industries for this type of sensors is smart farming. Another example is a smart industry. Another example is a smart cities or a smart parking even. So there are recently in many of the big cities, there are smart parkings that there are some sensors that are placed in somewhere near to the park area, and it will modify the police or some applications on your mobile phone, where there is a car park for you, or either the car park is busy or occupied by other cars. So there is a big potential in this domain, especially in industry. So another future direction for this backscatter communication is the NFC-enabled sensory information collection, which I am currently working on that. The idea is to collect these data from these sensors by some devices like our cell phones. For example, you can assume that in a smart city. So these sensors, as they need to communicate in a short range area, it's very hard for them to communicate with the one gateway in a far distance from them. So, but in the smart cities, there will be billions of cell phones in our hands. So the idea is to somehow manage these NFC tags to communicate with your cell phones. So as you may know, there is all the new Samsung cell phones or mobile phones are enabled by NFC technology. So you can do some payments with your NFC-enabled mobile phones. So they are already equipped in these mobile phones. So the idea is to collect this data from NFC tags with the backscatter communication, and then this communication, NFC has a different communication modes. One is the reader mode, and the other one is a peer-to-peer mode, which stands for the data exchange. So the idea is to collect this data by our cell phones and then communicate by some kinds of communication between these mobile cell phones. This data will be transferred to the server or to the center that they need this data. So yeah, just regarding the NFC, near field communications, you are knowing about these NFC technologies since it is already enabled in many of the smartphones. So, but the idea behind them is very simple. NFC-enabled mobile devices are actually communicating by a carrier, which is generated in 13.56 megahertz. So there is a coil in them. So depending on the size of the coils, this range can changes between the 10 centimeter up to 20-30 centimeters, but we can somehow enhance its communication range by some advanced technologies. Then this peer-to-peer communication can go, the coverage area can go up to 1 meter. So by this data exchange between the cell phones, it is expected that the data being transferred from the sensors toward the server. So yeah, what's the outcome, expected outcomes that from this NFC enabled sensory information collection? I suppose to have a massive data collection transmission using mobile phones without needing any private gateways or separate network design like Sigfox. So actually, it again saves or preserves the cost efficiency of the RFID tags and NFC tags. So it can bring the connectivity to the cheap power limited devices, losing backscatter communication through mobile phones, and also it's bandwidth efficient since it's a ambient backscatter communication. So it doesn't need any dedicated frequency spectrum. So yeah, this is the future research direction that I hope that we can find some colleagues that among you to work on this new direction. So, and thank you for your time and for your listening. And at the end, I just want to show you one of the potential journal publications that we can work on that. So just a moment. Sorry, what's that? I was hearing my voice. Can you see my screen, which is around the which shows the journal publication? Hello.
Not yet, Mahyar. Actually, we cannot see it.
Just let me. I think I need to share the Chrome now. Yeah, let me share the whole screen. Yeah, can you see now?
Waiting. So yes, I think we can see now.
Yeah. So this is a new journal. It's called Open Journal and Innovative Communication Technologies. Actually, it's a very interesting journal. And there is a special issue on ambient backscatter communications for highly power and spectrum efficient IoT applications in 6G networks. So as you can see, it refers to some ambient sources, RF sources like TV towers, cellular stations, and Wi-Fi access points. Then that they are communicating with the legacy receivers. So in meanwhile, there are some sensors that can utilize that spectrum or that RF signals without any dedication source or any dedicated frequency spectrum, and they can somehow exploit these things to communicate with each other. So you can go through this. This is the title, Open Journal on Innovative Communication Technologies, and it will give you the live comments from the reviewers as well, and it will be very helpful for, especially for the students. And these are the domains that this specific journal covers. So back to my presentation. Again, thank you for your listening. If you have any question, I'm here to answer your questions.
So thank you very much, Mahyar, for this great presentation and for the informative talk that you have provided and delivered to us. If there are questions from the attendees who are joining us from Microsoft Teams, they can ask whatever they want. If there are no questions, I want to ask some questions.
Yep. I think there is a question on Microsoft Teams, maybe. Can you read the question for me, Jihad?
Let me see the question. So here we go. So one question is saying, where can we put the reconfigurable intelligence? Where can we put the reconfigurable intelligence services in practical life? I mean, can we put it on walls or ceilings? So this is
So yeah, that's a very good question. So actually, these reconfigurable intelligence surfaces are at the early stage of design. So actually, as you can see, this is the first design in 2016 that I brought in this slide. So this is a very thin layer, so they can be deployed in on the walls, for example, as I proposed in this scenario. So this is a wall which is equipped with the reconfigurable intelligent surfaces sensors. So actually, this is for 2016. We currently have more advanced meta surfaces or intelligent surfaces at the time that I'm talking. So, but you can imagine that MIMO, just for a moment, ignore the reconfigurable intelligent surfaces. For example, MIMO currently we have a 64 antennas in a box of I think 1 square meter or even less than that. So since these sensors dimensions are very low, depending on the frequency that they are used for, so these sensors are able to be placed in different kind of materials like walls, like doors, or even some kind of windows. I saw one paper which proposed the new meta surfaces, so that there is a very clear glass, and even you cannot see those sensors that are placed between the glasses. If you go very close to that glass, clear glass, you can see some, the sensors, but from the far distance, you cannot see even those sensors. Was it clear?
Yes, thank you, Mahyar. Thank you, Mahyar, for the
You're
answer.
welcome.
Another question is that, do you know any companies who are using ambient backscatter communication technology in their devices or in their technologies?
Ambient backscatter communication is a bit different than the conventional backscatter communication. Actually, to the best of my knowledge, this AmBC or ambient backscatter communication is not still industrialized. But in some laboratories, in the laboratories, I think University of Washington, they already built some sensors that can communicate with each other. You can, I think, just Google it or on the YouTube, there are some introductory videos regarding those sensors which are built in the University of Washington, I guess. So that these sensors can communicate with each other, but still it's not industrialized yet.
Okay, thank you. So what's the biggest challenge that faces this type of technology from being implemented in the industry?
The biggest challenge is the failure in the communication due to the coverage range. So actually, as I said, they need to be very short distance from each other, these sensors.
I see.
So it's like a bar. You can imagine it's better than barcode, but it can be scanned from 10 centimeters up to 20 centimeters. So, and another problem is that it's not industrialized yet, is that because it's not standardized yet. So yeah, and there are some difficulties in the industry to move from the conventional RFID systems, and there are some doubts regarding whether this ambient backscatter communication cause any interference for the legacy receivers or not, because the frequency that they use is a license. Mostly they are licensed spectrum. So if they want to use those licensed spectrum bands, so they can have some new regulations and some permissions from the governments in each country.
I see. I see. Yeah, as we can see, it's a new technology, although it started in 2012, 2013 maybe. But like as is the case with any new technology, it has some advantages and disadvantages. And the goal of researchers basically is to try to increase the advantages of the technology and reduce the disadvantages by proposing new novel solutions, as Mahyar doing, as the other researchers in the world doing. But as we can see, it's very promising technology. It can really help us reduce the power consumption, make the communication more efficient because it doesn't require to use a licensed spectrum. You are already using the RF signals in the environment, and which is really exciting for some applications related to machine-to-machine communication and Internet of Things scenarios. So once again, we would like to thank you, Mahyar, for joining us today and sharing with us your latest research and research work related to this exciting domain. And we wish to have you again in some other webinars related to some other fields like waveform and modulation as well.
Thank you again. Thank you very much.
Thank you and take care, stay blessed and be safe.
Yeah, thank you very much. You too. Thanks everyone for your time.
Welcome, and thanks for the attendees, and especially for those who are watching us from YouTube. We are very sorry because of the buffering issue that was out of our control. It's due to low quality streaming, unfortunately, but we have recorded the lecture and we will be sharing it on YouTube very soon. Thank you. Take care and stay blessed, everybody.
Yeah, thanks. Bye.
Welcome. Hi, bye.